So as you're getting those things organized, let me just give you the kind of rundown of the plan for the next couple of days. I've said it a little bit before, and I'm going to say it again. Today is our big problem solving day, so some of that will be group problem solving, some of it's ranking class, some of it's just like number crunching and loving the physics. Tomorrow we're going to have an applied problem. You'll probably also get some AP workbook worksheets because it's that time of the unit. So those will come out tomorrow, and then we're going to finish this stuff up on Thursday. And then I promised you that quiz would not be on Friday because I know some of you have stuff going on Friday. So then on Monday of next week, there will be some sort of quiz-like thing, not intended to take the whole period, not intended to be super stressful, but just to kind of make sure that you know where you're at with this before a test at the end of the unit, right before the final. Yeah. So the quiz that you take on Monday, is that what you're asking? That will be over all of this. Yeah. So from equilibrium on. Okay. But to be honest, like that just basically started last week, right? Because like Thursday and Friday was kind of like laying the groundwork of things. Yes. Yeah. That where you needed to be. Okay. All right. Other logistical stuff before we get started? Okay. So yesterday we rewrote Newton's first law, and we talked about center of mass. So we're going to do a quick warm-up problem related to that. So I'm going to put it up here right now. Oops, you can't see because I froze. Bam. All right. So we've got an angler. You guys all know what an angler is, right? What's an angler? A fishing person. It's just a person who fishes. Yep. One who fishes is called an angler. Is balancing a fishing rod on her finger as shown. We say if she were to cut the rod right here, so you get a little fall out. The question is, would the weight of the piece to the left be greater than, less than, or equal to the weight of the piece on the right? I'm gonna give you just a minute to talk about this. Write down an answer. Just make some sort of commitment to yourself and to your table mates, and then we will vote. Woo-hoo. Okay. So, shall we just take a vote? I feel like votes are helpful. All right. So again, so we're saying angler is balancing the rod on her finger. So greater. So left hand side. That's over here. Is this one greater than, less than, or equal to the weight of the piece on the right hand side? So raise your hand if you think that this one is greater than. Raise your hand if you think it is less than the weight on the side. Raise your hand if you think it's equal to. It's okay. This is why we do this, right? No judgment. There are apps out there you can vote like anonymously, and I kind of wish I had one of those, but I'm not that organized today, so I apologize. But it was very clear that no, you're okay. It's okay. I want you to I want you to do this. So is it okay? Can we agree that less than is not the right answer? Okay, let's agree that that's true. All right, so we got greater than or equal to. You guys said you said equal. Can you tell me where you were at? It is balancing, right? That's the center of mass right there. Right. So right here, there's a thing, and I'm going to show you this right now because it's going to show up in another couple of problems in just a sec. For center of mass, they often will put a circle with an X on it. So that is the center of mass of that object. Does everybody agree that the center of mass of the object is on her finger? Okay. And so your thought process then was it's the center of mass. So what? So why are they equal? No, go for it.
Well, I just thought that if that was the center of mass, then them to balance, we both have to weigh the same thing on both sides, like how we put the ruler down.
Yeah. Yeah, it makes sense, you guys, right? That it's got there's something balancing over here that's balancing over here. That makes sense. TJ, you had your hand up. Were you going to say that, or did you want to say something else? Okay. Okay, so you're going back to the lab that we did on Thursday. Is that Thursday, Friday? Is that what you're talking about? Okay, so tell me how this thing relates to that thing. That they would be equal in weight? So, no, it's okay. Keep talking because what you're saying is helpful and interesting. So, okay, so I'm going to help you try and put words together because I think you're there. So you said that like this thing has to be equal to this. And you just said, but it's not, wait, we're talking about, what is it that we're talking about? Torque? Does that make sense? It's kind of a funny word, right? Like I kind of love the word torque. Okay, so we gotta put all the pieces together so that it makes sense. So TJ, I appreciate the way that you said it because it was like a very genuine like thought process. So something over here has to be equal to something over here. Is okay? And your gut feeling probably says at some point in all of our brains as we first looked at this question, well, they've got to be equal because it's balanced. But the reason that we do this problem is because it's not that the masses have to be balanced, it's the what has to be balanced. The torque. So the torque, do you guys like saying that word? The torque on the left has to be equal to the torque on the right. So how would we find the torque on the right? Force times distance. So you could break up all the little tiny pieces, right? Seems like a lot of work. Is this thing kind of almost uniform? It gets smaller. So, okay, let me back up. If this part was uniform, where would the center of mass of this part be? Right in the middle, right? Because it's not quite uniform, where is the center of mass, again, of the right side, where is the center of mass of this actually? Does that make sense? There's a little more mass over here because it's a little wider, so it's going to be somewhere like right here-ish. Does that seem okay? So I'm going to go ahead and put the center of mass of this thing, maybe here. Does that seem about fair to people? Is that too far over? I can move it over. You don't seem very happy with me based on your lack of affirmation. Is that okay? There we go. That's what I'm looking for. All right. This part is certainly not uniform. Where do you think the center of mass of this thing is? Somewhere in there, right? Depends on if the handle is, was somebody asking if it's made of lead or something? Like, it doesn't matter what it's made of because we know that it balances here, right? So if this is made of lead, this is going to be something pretty dense as well, right? But it's going to be somewhere in here-ish, yeah? So maybe somewhere in here-ish. I don't know where it is because I don't know what that handle's made of. But I do know that if I'm going to take all of the stuff on the right-hand side, it's going to really pull from right here. So this is the force of the right-hand side, the force of the earth on the right-hand side, right? Earth on right-hand side. And over here, this is the force of the earth on the left-hand side. On the left. But it's not the forces that we are saying need to be equal. It's the torque. And torque is what? We defined it yesterday, but it's been a while. Force times distance. You can say it with authority and excitement. It's totally fine. It is ready for you, and I want you to be you, okay? Like 100% for sure. Yeah, you got this. So this is going to be the force on the left times the distance of the left has to be equal to the force of the right times the distance of the right. This distance is a lot bigger. Do you agree? And if the distance is a lot bigger, the force needs to be a lot smaller. How are we doing? Okay. I love this problem because it's a thinker. You have to think a lot about it. Okay. All right. Here we go. We're going to do another one. We're just going to kind of keep cruising through. I've got a whole list of them. The more we get through today, the less we have to do later. This is definitely a not really. There are some of these that are very much physics one, but there's a lot of just kind of like number crunch kind of stuff. So I'm just letting you know. All right. Here's the situation. I took a standard meter stick, and I put it on 2 scales because why not? I guess I could have set that up and done that for you, and we could have looked at it, but you know, pictures are they work as well. Okay. The scales read 0.5 newtons each. The first question says, what is the mass of the meter stick? I'm gonna let you figure that out right now with your table. Draw yourself a picture if you need to. Do what you need to. There is no rotation in part A. Nothing to it. You can do this. I could have given this to you 2 weeks ago. All right, go ahead and figure out part A real quick. That is a great question. All right. So friends, part of the reason that I love the order in which we do things in this class is because we do something and then we take a little break from it. And now we get to revisit physics that we have done before. We just got to get our brains back in there. Okay. So in order to approach this problem, we just got to draw a Freebody diagram. So I'm going to zoom in, maybe. There we go. Woo, and I know I'm frozen, but I'm going to unfreeze it. There it is. Whoa, okay. Now, remember that before we used to just draw all of our forces from that one dot, right? But now we're acknowledging that objects sometimes have width or length or height or whatever. So I'm going to draw forces that are acting from the system just being the meter stick. So tell me what forces are acting from on the meter stick. Give me one of them. The force of the earth. Tony, is that you? Which way does the force of the earth go? Oops. Goes straight down, right? Okay, so the force of the earth on I'm just going to call it the stick because I'm lazy. And that's F sub G. All right, that's one force acting. Are there any other forces acting on the meter stick? Go, Bo. Okay, so normal forces exist because you have a surface pushing up, right? So where is there a surface pushing up on that meter stick? The far right and the far left, right? Absolutely. So we've got two of them. Whoa, oh my gosh. It's like I have magical fingers that make things happen. Who knew? Okay. So this is the force. I'm going to say the force of scale 1 on the stick. And you can call that a normal force. In this case, just because I'm trying to differentiate between the forces, I'm just going to call this force sub 1. Does that make sense? Just to differentiate it from the other one that we'll probably call force sub 2. And then we've got another one over here. Is this kind of what you're thinking, Bo? Force of stick 2 on scale 2 on the stick. And I'm going to call that just F2. All right. There's my really lovely Freebody diagram. And again, I'm not saying you have to have drawn a Freebody diagram to solve part A, but it's kind of helpful. All right. So we got 3 forces. Can we write down an F net equation? Well, sure we can. It's been a while since we've done this, but you may remember that it's pretty important to be able to do it. So let's try it out. F net, these are all in the Y direction. So if you want to mark that it's in the Y direction, you're certainly welcome to. What forces do we have acting? Easy answer here, friends. What you got? Force of gravity. What else? Force of F2 and F1. Yeah? Green. Oops, I wrote that wrong. Sorry. Oops. Silly Miss Carveling, getting ahead of myself. And those forces have to add up to what? Indeed, how do you know they have to add up to 0, friends? There you go. Bam. Okay. If I've got 3 forces that add up to 0, what do we know has to be true of at least one of them? Has to be negative, right? I know that I'm doing this kind of slow, but I'm doing it because I want to make sure that you get all these pieces. Because the next problem and the next few problems that we do, you're going to have to chew on this a lot. I really want to make sure it makes sense to you. All right. So in this case, I can solve for FG, right? These are both 0.5. I'm going to move them over to the other side, which means that FG equals 1 Newton. You with me? FG equals, as we were just talking about, the mass times the acceleration due to gravity. We know little g is 9.8. So the mass of the meter stick, which is the thing we wanted to know, is going to be 1 Newton divided by 9.8 meters per second squared. The negative here has been taken into account over here. Okay, you only have to take it into account once. What's the mass of my meter stick?
You have a calculator out, friends. You can do it. Do the division. 1 divided by 9.8. There you go. How many sig figs do you want there, Tony? My goodness. 0.1 maybe? Maybe a couple. How are we doing? Everybody happy? So this problem right here, part A, as I said, is something that we probably could have figured out 3 months ago. Part B is where it gets fun. Part B says predict. Now sometimes predict has loaded terms, right? Like just like guess. I want you to determine which or what each of the scales will read if we place a 5-kilogram brick 40 centimeters to the right of the left scale. So if you have not yet drawn this picture on your notes or wherever you're writing things down, then you might want to do that, okay? I am not forcing anybody to write this down, but I would encourage you to. So 40 centimeters to the right of the left scale. They kind of have them marked out here. 1, 2, 3, 4. So it's like here. So there's my brick. So maybe this is an easy question. Maybe nothing changes. Is that the right answer? Do you think that the scales will still read 0.5? If I place the brick not at 40 but at 50, how would the scales compare? They'd be the same. But because I put the brick over here, what does that maybe mean? This one's going to read more. Is that kind of what your gut is telling you? That's what it should do. Yeah. Do you want a minute to see if you can figure it out? Or do you want me to jump in with you? You want a minute to work on it? I'm going to give you a minute to work, or maybe, a couple minutes, and then we'll discuss. Give it a shot. I love your enthusiasm, you guys. This makes me happy. Before we go on and actually do this problem, I do want to say that I'm really excited that you guys were ready to dig in and try it out, because that's the thing. These problems are a little weird. So tell me about your initial problem-solving process. Can you tell me like where you started, what you did? Because I heard a lot of good conversation. Yeah, Shushma, what did you do? Okay, awesome. I'm gonna move this out of the way because I'm just gonna move it over here. Oh, okay, so I'm just gonna move it. You can't see it, but haha, now it's moved. Yay, okay. So you drew a force for the brick, okay? And which way did it go? Okay. So tell me why you did 1 down and 1 up and what the forces were. Okay. So the force of the earth on the brick, something like that. Okay. Okay. So you had a force of the stick on the brick or something like that. Okay. Awesome. So part of the game when we're doing these problems is that we have to be able to assign or to state what our system is. Okay. And the first in part A, what was the system? What was the object that we cared about? What's that? Just the meter stick, right? But now we've added the silly brick to the situation. If we look at these two forces that Shushma just said on here, they are both acting on the brick itself. But the brick isn't being affected by the scale. Are you guys with me there? Okay. So it's not wrong to have done it that way, but I think it's going to be more fruitful for us to actually make the brick and the stick all one system together. Does that make sense? So if we talk about them all as one system, then we've got the force of the earth on the brick part. We've got the force of the earth on the stick part. And then we got the force of the scales on the system as well. Does that kind of make sense? So if we do that, I'm going to take this top force out. Is that okay? I agree that it absolutely is there. But again, as we said, if we're going to take, oh, hello. If we're going to take the brick stick, I did not intend for those to rhyme, and it's kind of goofy. But the brick stick system, then we would call that just the force that's acting on the system. Okay. we drew a force. What else did you try and do? Is that as far as you got, or did you get further? Don't be afraid to tell me stuff. You guys are smart people and you've got good intuition. Go, TJ, what you got? I love it. Great. So why didn't you have your hand up too, Goofy? I'm just teasing. That's okay. Oops, not FG. Hello. You said FNet. So given what you did, TJ, and what we have up here, can we put together an FNet equation together as a group? All right. So help me out. What do we got? FNet. What's acting? What you got? FG. So the force of on the stick. So I'm actually going to relabel this because I'm going to get confused otherwise. I'm going to call that the force of the stick, and I call this one the force of the brick, or the force on the brick. Is that okay? Just to kind of keep things. So I'm guessing, Lucy, but I don't want to put words in your mouth, that by FG you really meant the force that's acting on the stick. Is that true? Okay, awesome. What else have we got? F1 and F2. What's that? Okay. I'm just here to help you. Any other forces acting? The force of the brick, absolutely. And friends, what do those forces have to add up to? Indeed they do. They have to add up to 0. Now, we, and by we I mean I, have been very lazy when I've written out FNet equations a lot of times, and I forget to write my negatives in there. But now is the time when we really got to pay attention to negatives. So which of these 4 forces are negative? Bless you. The force of the stick, or force on the stick? Anything else? And the force on the brick, absolutely. Okay. And I have to remember what the question asked because I don't remember. Predict what each of the scales will read. So what are we really looking for? What are our unknowns in this? F1 and F2. Here's the trouble, you guys. There are 2 things we don't know. You know from mathematics, I would imagine, that if you have 1 equation and 2 unknowns, can you solve that? No, you've got an infinite number of possibilities, right? In order to solve an equation with 2 unknowns, or in order to solve a problem with 2 unknowns, how many equations do you need? 2. Lucky for you, yesterday we wrote down a situation that has to be true if something's in equilibrium. Is this system in equilibrium? Look back in your notes if you haven't done so already. What is it that has to be true besides FNet being 0 in an equilibrium situation? Have you looked?
Look it up.
What? The torque has to be 0 as well. Yes, it does. All right, so let's write the torque. So torque net also has to be equal to 0. So here's the thing, my friend. Whenever you're going to solve these problems, if you have 2 things you don't know, you have 2 equations, and the second one is going to be the torque equation. So for every force that exists, there is a torque. Okay. Remember we said yesterday, or I think it was yesterday, that the torque that's acting is any force times the distance that we are from a point of rotation, right? So that's just a friendly reminder for a moment from now. But for any force, there is a torque. So just like I wrote out the force net equation, that's the equation, I wrote out the torque net equation, the torque net equation. Here we go. I'm going to do them one at a time. So I'm going to do the torque from the stick, and I'm going to add, I'm just putting them in the same order that they were before. The torque from 1, and I'm going to add the torque from 2, and then I'm going to add the torque from the brick. So far, so good? You're like, that's it. That's freaking all kinds of new things. Thanks a lot, Miss Carberry. We can figure out, though, if some of these can go away, maybe. There's some beautiful things that will happen. We need some positives and negatives. Remember, we did positives and negatives here. we talked about how to do positives and negatives for rotation. Do you remember what we said was positive and what we said was negative? Clockwise is positive, yeah. Clockwise is negative and counterclockwise is positive, right? Okay. So now the question is, which way would it rotate? What does that mean? Is this thing rotating? Is there even an axis of rotation here? I don't see one. So this is a big opportunity for you guys. I don't know if you remember that when we were doing gravitational potential energy and we talked about how you could say your H equal to 0 wherever you wanted it. Do you remember that? You had all of this, like the world was your oyster. You got to pick wherever you wanted. Same situation here. If you have something where everything is at equilibrium and you're going to use torque to solve it, you have to pick an axis of rotation. But you can put that axis of rotation wherever you want it. There are some choices that are better than others, and we'll talk about which ones are better than others. But you could put your axis of rotation any place on this system. Okay? Wherever you want it. But I want to remind you that we're trying to find F1 and F2. Are you with me there? Okay? And if we happen to put the axis of rotation, the place that this thing would rotate about if one of those forces was taken away, what happens to the torque for F1? Remember, torque is force times the distance from the axis of rotation. If I put the axis of rotation right here, where does it go? It goes to 0. Are you with me? If I put it right here, then the torque of this one would be 0. But we already know what that one is. Same for here. I could also put it here, and that would be another rather good choice. If I could put it here, then I just have to solve a system of equations, right? Like you could do it. Your math teachers would be excited. But, I mean, and you can do that if that makes your heart happy, then you know, do whatever you want. I'm going to make a suggestion that for, at least for this first one, that I'm going to put my axis of rotation right there. Okay? So I'm going to put my axis of rotation on F1. The nice thing about that is, again, because torque is force times distance, torque 1 is now 0. It goes away. See ya. And once we've set our axis of rotation, then we can figure out what other things are, if things are positive or negative. So now we're going to imagine that we put an axis, like a rod, through this side, okay? And now only the brick is causing this thing, causing forces on this thing. Where is the brick going to cause it to rotate? Down, clockwise, or up, counterclockwise? Down, clockwise. So that means that this thing right here, this torque, would be negative. Yes. Yes. So this torque is a negative torque. Let's look at the next one over. So again, my axis of rotation is right here on F1. Is this going to cause a negative or a positive torque? Negative. Again, it's kind of hard to see this, especially the first few times you do it. So imagine that the other forces aren't acting. If there's a rod through here, this force right here is going to pull it down. That's where the negative is coming from. Okay, so it's going to go clockwise, which is also negative. So that's going to be a negative torque. We've got two that are negative, one's at 0. This one's hopefully, fingers crossed, going to have to be what if they add up to 0? Positive, but let's just double check. So I'm going to put my axis of rotation here again. This force, if it was the only thing acting, would cause the whole system to go up. So that would be a positive torque, okay? So there we go. I'm going to just make that positive just so we didn't forget to do it. How are we doing? We okay so far? I know I'm kind of walking this through slowly, but I'm trying to kind of get you there because if you get lost, it gets really unpleasant, and I don't want to lose you. All right, so I'm going to go 0. I'm just writing this down. Shoop, shoop, is equal to, instead of writing torque, I'm going to write force times distance. Okay, that's all I'm going to do. So now I'm going to say the opposite of the force of the stick times the distance of the stick. Literally just writing it out piece by piece. Remember, this is not really how AP is going to have you do it, but to understand what they're going to ask you, this is a really nice way to kind of dig in. Plus the force of scale 2 times the distance to scale 2, plus the opposite of the force of the brick times the distance of the brick. How's it going? You okay? Let's see what things we know here. I know the force of the stick, right? We figured that out because it's the mass of the stick times gravity, right? I know the distance from the axis of rotation where that force is going to be applied. How far away from the axis of rotation is this force applied? 50 what? 50 centimeters. Yeah. 50 centimeters. So I know those two things. Do I know force 2? No, that's one of the things I wanted to know, right? Do I know the distance for 2 though? Yeah, how far is it? 1 meter or 100 centimeters. It doesn't matter if you use centimeters or meters, friends, as long as you keep it consistent. I don't care. And then the force for the brick, you know, and the distance for the brick is 40 or 0.4, depending on again if you're doing centimeters or meters. How are we doing? Can I let you go for a moment? Do a little math. Once you've figured out F2, you can use that value right here on your F net equation and then solve for F1. Okay? I'm gonna let you chew on that for a little bit because I think you're there. I think you can do it. All right. Let's compare our answers, shall we? So again, just to kind of reiterate, the force of the stick times the distance, the distance of the stick, plus the force of 2 times distance 2 plus negative, do we catch the negative? Force of B times distance of B. Can you all help me out with what'd you get? What'd you get for an answer for the force of 2? You got 20.1. I'm not saying it's right or wrong, I'm just asking. Sid, what did you get? You got 20.1? Yeah? Should we go through it quick? Would that be helpful? Would anybody like me to go through it? Because I'm happy to. Yes, please? Okay, let's do it. So you guys have to help me out with the numbers because I don't have them all written out here. All right. So the force of the stick, so it's going to be the negative of 0.1 kilograms times 9.8 meters per second squared. Is that okay? That's the force for the stick times the distance, which was, are we doing it in centimeters or meters? I don't care. Meters. All right. So 0.5 meters. And then we're going to add to that F2 times a distance of 1 meter. Oh no, I'm going to run out of space. Oh no. Oop. All right. And then we're going to add to that negative the force of the brick. And I don't remember how big the brick was. It's 5 kilograms. So that's going to be 5 kilograms times 9.8 meters per second squared times a distance of, is it 40 or 0.4, excuse me, meters? Help me out to make sure I'm not making silly mistakes. You okay with that? That has to equal 0. So move the brown end and the orange one to the other side and then divide by 1. Okay. That'll give you 20. All right, my friends. I want to say thank you very much for paying attention today and being engaged. It was kind of a low day, but hopefully we got something out of it. See you on Wednesday.